you look at this circuit here, oh, I gotta get out of presentation mode. Doesn't work. Please work. Ah, perfect. If I were to look at this circuit here, all right, and forget about that I have this VG here, that's a galvanometer. It's basically a voltmeter. But let's say I had a circuit, a resistor here, and this circuit has resistors at R1, R3, R2, and this unknown one, Rx. And if I were a current, I would be coming out this way. And what are my choices at the node, at the A node? Where can I go? Left and right? Is that good? You guys know that? I can go left. I can go right. But then once I get to junction D, what are my options? Yeah, I can go through this resistor. I can go to the right, or I can go towards R2, and then I can go back to my battery. However, if I were to go to R3 now, if I want to go in this way, and I'm at junction B, what are my options? Which one? Rx only? So you said, and you weren't wrong, you said that when I went to D, I can go right and I can go down. When I'm here, why can't I go left? Or can I go left? Yeah. But there's two resistors there. So this resistor and this resistor, or one resistor here, it's not really going to know the difference. They're both, neither of them offer a no resistance path. Right. Again, like I said, it's a matter of, like if I had two resistors like this, I'm still going to get a current in both branches of my circuit, right? But if this one had no resistor at all, then you'd be right. Then there is no resistance there and no current, all current would go through there. And none of it would go through those two resistors if there was no resistor in this section here. But in this case, there are resistors. So which one is it going to choose to go through? Rx is going to definitely go through here and no current is going to go through here. Well, that's what we're trying to figure out actually. So in reality, there is a current that goes through there, and we'll figure out why. But essentially, we can't use regular parallel and series circuit math to be able to solve this one. We can't say that this resistor in the middle is necessarily in parallel or in series, or how it is in parallel and which other resistor it's in parallel with. That's actually not going to be possible. All right, so we have to use a different method to figure this one out, and that's what today's lesson is about. So what we're going to do is we're going to figure this out mathematically, and then we're going to go upstairs and figure this out experimentally. Okay, and the whole idea behind this the ultimate goal is to measure this unknown resistance. Now bear with me, that's kind of weird because you can just plug in a resistance meter and figure out what the resistance of a resistor is, but you want an accurate mathematical measurement, and this is going to be the best way to do that. So let's move on. So here it is. A Wheatstone bridge can be used to measure an unknown resistor. That's really the most important part of this, right? That we're measuring an unknown resistor to figure this out. We're using a Wheatstone to figure out an unknown resistor. All right. Let me ask you guys a question. My current comes here through this circuit, all right? And it makes a stop at this junction. And at some point, it comes back in at the end, and it goes back to here. What would be, if this is a 5-volt, excuse me, if this is a 5-volt battery, what would the voltage be at the top here, at this first node? It'd be 5. And what would it be here? 0, exactly. All right, so that means there's a voltage drop of 5 volts across here. And when there's a voltage drop, then there's a current, right? If I were to tell you that, okay, there is a part of this circuit that is 5 volts, and it goes somewhere, and it's connected to another 5 volts, what's the current through those two, between those two? It's not 5, I'm talking about the current. if there's an electron that's somewhere in between these two, which one is it going to get attracted towards? The left one or the right one? Well, right now there is only one way to go. It's either left or right. So you're an electron right here. There's a 5-volt potential here and a 5-volt potential here. Is this electron going to go there or there? Which one is it? Is there a force that's attracting it? There is no force. It's going to be stationary. So if the electron is stationary, what could you tell me about current? Zero. The current is zero. So if there is a voltage difference of zero, if this was 5 and this was 5, then there would be no current. But because this is 5 and because this is zero, then there is a current between those 2 points. Now, here's what I'm trying to say now. You would consider the term that we use to to describe a situation where in a Wheatstone bridge, and this is what a Wheatstone bridge circuit looks like, if this voltage A and this voltage B are equal, and we call this VAB, and if the VAB is 0 volts, then no current is going to pass through this voltmeter. There's no current that goes from left to right. Okay, and we call this a balanced circuit. And the way to create a balanced circuit is to make sure to maintain this ratio, right? And these are using terms that are described in this Wheatstone circuit here. So this is called a balanced circuit. And the reason why we call it a balanced circuit is because there is no current that travels through the middle, because the voltages at VA and the voltage at VB is going to be the same. And therefore no current goes between them. And if you want to create that experimentally, then you have to use this ratio to establish. Yep. It doesn't have to be zero, no, but when it's zero, we call it a balanced circuit. Then we don't call it a balanced circuit, and there's some math to do, and we're going to do that. Yeah. All right, so if we're to redraw this circuit, because you guys are going to have to redo this upstairs in practice, this is what the circuit might look like. All right, now there's many different ways of doing this, and it's actually quite fun. Yesterday I was watching the students in the other group do it, and some of them were using like 10 jumpers to be able to do this, and some of them were able to reproduce this circuit with no jumpers at all. It'll be like a challenge once we go upstairs and try it out. Um, but um, but it can look differently based on the situation. I might, for example, on a lab test, show you a circuit that kind of looks like this, and ask you what kind of circuit it is, in which case you tell me it's a Wheatstone circuit. All right, moving on. So the whole purpose of this is to calculate the voltage across this bridge. It's called a Wheatstone bridge because there's this bridge in the middle, and we want to know what the voltage across that bridge is in this situation. I'm going to tell you right now, this is not a balanced circuit. All right, so there is going to be a voltage difference across that bridge. But this is pretty easy to do because I can just ignore this voltmeter here because that's how I'm actually experimentally measuring that voltage. So now really all I need to do is measure the voltage or calculate the voltage remaining at point C and calculate the voltage remaining at point D. So before we do that, what is the voltage at point A? Good, 100 volts. What is the voltage at point B? 0. Very good. All right, and we have an equivalent resistance on the left, which are these two series, these these resistors in series or in parallel? In series, so I just add them up. So my equivalent resistance on the left is 200. And what about on the right? 640. All right, and now we can figure out what the current is on going onto each side, or we can figure out what the total resistance is. So Req is going to be equal to 1 over 200 plus 1 over 640, or all that to the power of minus 1. If someone can give me an answer for that. How much? 152 ohms, and therefore I can calculate my total current if I use my total voltage. So 100 volts is equal to I times 152. Therefore, I is going to be equal to something like 0.6. 0.7? Use a 656, so let's do 6.66. That's my total current. And if that's my total current coming in here, I can figure out what my, is it ground shaking? Oh, okay, sorry. I was like, this is scary. Like, no, the whole table was like, so okay, so my current here is 0.66, and I can figure out what the current going in each section is. So I can figure out with my equivalent resistance on the left and my equivalent resistance on the right. So it'd be V left is going to be the same thing as the V total because it's in parallel. So V left is 100 volts. It's going to be equal to I left multiplied by the resistance of the left side, right? So I'm just talking about the left side here. And so the voltage is going to be 100 volts is equal to the current going through it, which I don't know what it is, multiplied by 200. Therefore, I can figure out that my I is 0.5 amps. You guys understand how I got that? Yeah? So I can do the same thing on the right, but I don't need to because I left is just going to be I total minus, sorry, I right is just I total minus I left. So I can say that I right, too close to the bottom here, I right is going to be equal to 0.16. All right, perfect. So let's figure out what was my voltage drop across R1. So this has got a current of 0.5 amps. So 0.5 amps times 80 ohms is going to be 40 volts. So 100 minus the 40 volts that I dropped here, I can figure out that my voltage at point C is 60 volts. What's that? Yeah, sure. So I figured out the voltage drop across R1 because I have the current passing through it and I have the resistance. So I can use Ohm's law. So this is 40 volts. And if I had 100 here and I lost 40, then that means I have 60 left here. Okay. And if this one had 0.16 amps passing through it, through a 480 ohm resistor, I can also figure out the voltage drop there. So what was, can someone calculate that? I can't do that one in my head. 1/6 of that. 80? 76.8. So let's do 77. So there's a 77 volt drop across that first resistor. Therefore, what's going to be my voltage at point D? 23 at point D and 60 at point C. So if I were to calculate the voltage difference between point C and D, what would be my answer? 37. Okay, so the answer here would be 60 volts minus 23 volts. That's equal to 37. And so if I had a resistor there, would there be a current going through it? Yeah, absolutely, because there is an unequal voltage distribution. Now the second part of the question is, what does this resistor R4 need to be if I want there to be no current across there, if I want the voltage difference to be 0. There is some complicated math to do, but if you go back 2 slides, we can use this relationship here. So just try to figure that out. So I'm trying to create a balanced circuit. And so the ratio between R1 over R2 should be the same as the ratio between R3 and R4. So let's go back now. So what does R4 need to be if R1 over R2 is to be equal to R3 over R4? And that's if I want to, that only works if I want to create a balanced circuit. $720? Okay. I believe you. I think that's the right answer. So if you wanted to create a balanced circuit such that there is no voltage drop across C and D, then you would replace R4 with a resistor of 720 ohms, and therefore you would create something called a balanced circuit, and there would be no current across the bridge. If it was balanced, absolutely right. Okay. All right. Example 2. What I'm asking now is calculating the voltage drop across that 100 ohm resistor in the middle. All right, so now it's going to be a little bit more complicated because I can't ignore what's in the middle. It's not a nothing. And so if there's a nothing, if there's nothing there, right, it would be easy. We'd just do the method I just talked to you guys about. But right now there is a resistor there, and we have to use a different method. First of all, is this circuit balanced? Is it? Well, it would have to do with these 4 resistors. It's not balanced. Okay, so we can't go back and use, I can't say that the current in here is 0, right? If my resistors were balanced, if my circuit was balanced, then I could automatically say that the voltage drop is 0 and the current is 0. But we can't say that in this case. So there's a method to doing this, and it's long and kind of complicated. So we'll try to do it slowly, we'll try to do it together, and ask me questions if you get lost along the way. The first thing you want to do is ignore the middle resistor and calculate REQ. So let's go back. Let's calculate REQ, ignoring everything in the middle. So that would make it these two in series. So it's going to be 450 on that side. And these ones in series, so it's going to be 300 on this side. And REQ is going to be 1 over 450 plus 1 over 300, all that minus 1. $900 over 5 is 450, no. 900 over 5, what is that? 180? So my REQ is 180. That's step 1, done, 180 ohms. Step 2, solve the circuit in terms of its voltage drops across each resistor and the current across each resistor, just like we were to do using Kirchhoff's law, Ohm's law in the past, ignoring the middle one. So continuing along the same path of ignoring that one, I can figure out my total current. So V total is equal to I times REQ, or I total rather. So I have 24 volts is equal to I total multiplied by 180 ohms. And therefore I is going to be equal to, no idea. How much? 0.13? So that's my current coming out of here, 0.13 amps. I can figure out my voltage drop across each resistor. So if this was in parallel, therefore this is going to have a 24 volt start and a 0 volt finish. And I can figure out my current going on the left. My current going on the left is going to be 24 volts. This is exactly like what we did in the last slide, right? You guys are following me? Just need a number for this. Oh, 0.053. Yeah, that makes sense. And I write, it's just going to be the total current minus that. So can't do that in my head either. 7.077. I figured out my current going in each direction. I can now figure out my voltage drop across each resistor. So if this is going to be 0.53, I can figure out what my voltage drop is for that first resistor there. Can someone do that for me? How much? 7.95 volts. And therefore, by subtraction, I can figure out that this is going to be 16.04 volts, 05 volts. Can you guys do the same thing for the right? Here? So this, the current going through it is 0.077 amps. So that times that is 4. Okay. It would have to be 20, right? I could have made a mistake, but this plus this should give you this. Did I make a mistake? Could be a rounding thing. Did you 24 divided by 300? That makes sense. So how come we got different numbers? No, but back up here. So I think there might be a mistake with this. So 24 divided by 180, is that correct? 1.5, 1.3, 0.13. And then here, do we do this correctly as well? It's 5353 or 5333. So if it's 5333, that still shouldn't make a difference because this one's going to be exactly 24 divided by 300. It should be exactly 0.08. I did the math wrong somewhere. Is there REQ Did we round our REQ maybe? That's not a rounded number? Strange. What's that? Oh yeah, does it? Okay, all right, so it's a rounding thing then. All right, okay, that solves that. All right, so okay, now we need to figure out, okay, so we've done step 2, all right? Step 2 was solve the circuit, finding the voltage drop across each resistance. We just did that. And now we need to figure out what the voltage drop is between those 2 points that I have here. So I'm going to call this point A and point B. And so what's the voltage at point A? It's written somewhere there. Exactly, 16.05 volts is the voltage remaining at point A. And what about point B? 20 volts. Okay, well, let's stick with 20. And here I'll stick with 16 just for argument's sake. Okay. So I have 16 volts and 20 volts. Is there a voltage difference across A and B? Therefore, there's going to be a current through it. That's great. And what is that voltage difference between those two? 4. So here, find the voltage difference between VAB. So in this case, it's going to be 4 volts. Okay. And then here, we're going to redraw the circuit in such a way. So this is the complicated part, all right? So follow very carefully here. So we're going to redraw the circuit. We're going to redraw this circuit, except we're going to remove this battery, okay, and connect it with a wire so that it's not empty. And we're going to remove this resistor and replace it with a battery of the voltage that we just calculated. Let me redraw it over here. So what we had was we're going to remove the middle resistor, replace it with a voltage source of VAB. So it's going to be like this, 4 volts in the middle. And then here it's just going to be connected by a wire. And that's it. John, you have a question? Okay, it kind of does actually. Which one has a higher potential, the 20 or the 16? The 20. So this side is going to have the positive side of the battery. Okay, so it's a 4, but you see how my positive is going to be on the right here, and the negative is on the left? Yeah. 16 and the 20 is the voltage that's remaining at point A for this resistor, and this is going to be the voltage remaining for this resistor at point B. Exactly. Okay, perfect. So now we got this resistor here, this system here, and I'm going to rewrite my resistors. This is R1, R2, R3, and R4. And I could kind of figure out the new circuit that I've drawn. That's what I've done here. I've redrawn it into this more simplified method. So here we have our current that starts at the battery, goes to this point here. Then it's got a split between R3 and R4. So there's your split between R3 and R4. And then it can choose whether it goes through R1 or R2 by going around this bypass or by going directly through the next resistor. So the next two are going to be in parallel as well. And I've finished my circuit back to the end of the battery there. So I'm going to read the steps. We just did all those 3 steps in one. So we calculated the total equivalent resistance again, we're going to. Once R1 and R2 are in parallel, so you can see R1 and R2 are in parallel. or 3R and 4R in parallel, and that the voltage source, the battery, is the voltage difference that we calculated across points A and B. So now we have to find the new REQ. So this one here and this one here, we can find those values. So 1 over 150 plus 1 over 300. And here is 1 over 50 plus 1 over 250. Did it change? No. It's not the same. Yeah, it's not the same drawing. This is R2. And if you go back here, R2 is 300. Oops. Can I have the equivalent resistance for the top part? 100. And the bottom part? How much? Okay. Let's do 41.7 for. Okay. And obviously, if I wanted to find the total equivalent, it would be 100 plus 41.7, which would make it 141.7. All right, we're still not done yet. Step 5, now that you've calculated the total equivalent resistances, so these are the two that we just calculated, you're going to add now that original circuit, that original resistor that we removed, you're going to add that in series into the circuit, into this new circuit. Because remember, now we have a 4-volt battery source, not a not the 100, was it 100 or 24 that we started with, not the 24 that we started with. Now it's the 4 volts that we calculated. And finally, as you've done this, after half an hour of doing mindless math, you can find the voltage drop across this resistor that you're looking for using regular. So REQ is going to be equal to 241.7 ohms. The voltage is equal to 4 volts. I is going to be equal to 241.7. Oops, 4 divided by 420.7. Yep. Oops. Perfect. And so that's because these are all in series, you can say that that's the same current going through all of it. And now we can calculate the voltage drop across this one here. So it should be about 1.7 volts. That's our answer. Yeah. Let's put that into practice. So same principle. You guys do this one on your own. Calculate the voltage drop across 100 ohms. Step one is to calculate REQ by ignoring the middle one. Someone find REQ? Ohms, right? I heard volts. So step 2 and 3, I'm gonna let you guys work on this together. I want you guys to tell me what the voltage drop is across points A and B. Does someone find VAB? What'd you get? 0.34? Does anyone agree or disagree? 0.37? 0.35? I guess it might just be a rounding issue at this point. So I'll take the average, 0.35. So now, step 4, you got to redraw your circuit. Oh, no, I drew it wrong. And I got the equivalent resistance for the top 2 resistors there in the new circuit. What? 4.5? Sorry, repeat the first one again. I think you made a mistake there because it can't be higher than 50. 37. Oh, I see. Okay. Okay, very good. Step 5, put the other resistor in series. The total currents, does someone have it? The current in the new circuit, in this one here in the bottom right. 0.00495? 195? That sounds about right. Oh, okay, I see. And so therefore the voltage drop is going to be 0.00175 times 100. 0.175. That's pretty close to the answer. It's a long process, but pretty straightforward, I think. Is there any questions about this? Well, here's another example of something that I can ask you. Okay? Let me just wait until everyone's done. We're going to get to that. Good? Is everyone done? Any questions? So what is the voltage across R4? This is kind of a trick question. What's the trick here? Zero? It's not zero. It is simple though. You don't have to do all that complicated stuff that we just did. How about you try to redraw this circuit? You got your voltage source? Okay. You got your voltage source? Yeah, exactly. So you got R1, R3. They join up. And then you have, because these are connected, you have the option of going to R2 or R4. And then going back. And you guys can solve this one pretty easily. I'm not really too worried about it. You combine and you find the equivalent resistance for each resistor, for each parallel part. So you find an equivalent resistor for this. You find an equivalent resistor for this. You find the total current, and then you find the current going into each one. Yeah. It's just how you label them. It doesn't really matter what number they are. Right. You're talking about here, right? Or here rather, in that step. Yeah, we put this one parallel with this one, and then here we put them this parallel with this, right? And that's different from this. Why? Oh, okay, I see what your question is. Yeah, when we did this, when we did step 4, our voltage source is in the middle, remember? And so then, okay, let's go back. Where did I have that drawing? Oh, here. Up here in the top, I put my voltage source in the middle, and I shorted the battery, which I made a wire there. So if I was a current, I'd be going into this node. Then I have the option of going into R3 and R4. Then once that, let's say I took R3 path and I came here, I have the option of going into R1 or going all the way around and doing R2 before going into the battery. All right, so if you did the calculations, the answer here is 18 or 19 volts or something like that. Now here's the application part. I'm taking it a bit one step further. So here I have a Wheatstone bridge, or a temporary Wheatstone bridge. And I'm actually going to make it a slightly bit more complicated by adding, instead of having a switch here in the middle, I'm going to have a switch and a resistor in the middle, right? So in this here, there's going to be another resistor. It's going to be 100 ohms. And there's a switch. And what I'm asking you is to determine the brightness of the bulb, of all the bulbs, before and after the switch is closed. Okay? So that means that you need to determine the current that's going, or at least the voltage drop into each one, voltage and current going into each one to figure out what the brightness is. Because remember, brightness is power, and power is equal to voltage times the current, or current squared times the resistance. What I want you guys to do is, it's very strange. Maybe you guys can explain this to me. When I think it might be this classroom, when I tell the other group to do this, they get into groups and they're doing it. I'm asking you guys to do this into groups and you guys remain quiet. So I want you guys to do this in groups. But how could I make it so that you guys are motivated to do that? Like the other one's like automatic, and you guys prefer to work alone. Work together. What doesn't matter though? Helping each other is really important. One of your competencies in this course is group work. Actually, in all science courses, one of your competencies is group work. And here we are. I don't pretend to be the best at explaining things, right? So maybe you guys can explain it to each other better than the way I explained it to you. Maybe I explained it to someone who understood, and then you guys can explain it really well to the people around you who may not understand. Right? It's really important to be able to do this. It's beneficial for both of you because one, you hear it from a different way, and two, by explaining it to others, you get. Do it together. Okay? Determine the brightness of the bulb before and after. Absolutely. Yeah. The voltage drops. Say that again, Mark? I'm not sure that works. Why not? Well, it's not necessarily. Because like, I mean, like, you know, that's fine with total. You can only do 9 volts, 8 volts, for example, on the left side. Okay. Times 150, then you get your. Oh, I see. Yes, you're right. Yep. Okay, I think it might just be a rounding issue. If we round it, if we got 195. What was your voltage? You got 1.6. Where's what's the current source? I think you're missing the zero current. 4 divided by 241. So you grab this, we all got this. Oh, this is the example before. All right. Let's take that control. Somebody there, right? Or 1.6 volts. It's totally different problem. Different numbers. Okay. Okay, I think maybe my handwriting might have just been better. Yeah, so this is depending on what you use for this number, you had a different number for this. Right, and when we were doing it, when we got it up here, where was it? When we did it up here, some of us got 0.34, some of us got 0.35, some of us got 0.37. So it just changes around there. So try 0.34 or 0.37. Okay, so let's see how I got that. You continue to the new problem and I'll try to figure this out. I don't have the answers. The brightness should. So this is when the switch is open. Okay, we'll go in after the switch is closed and I'll plug it. Someone have a second calculator? So, and sure, the answer is quickly 190. Okay. Yep. It's gonna become a weak sauce.
Oh, okay, so we have to do like,
All that.
yeah, but there's no resistance in there.
I added one.
Oh, okay, you added it.
Yeah. So I'm just gonna look this side. I added a 100 ohm
Oh,
resistor.
okay.
You got an answer? Oh. Okay. Yeah. Okay, so redrive that looks like this. But don't drive it.
Yeah, but when it's open, it doesn't matter. It's only when it's closed. When it's closed, it's like a brick. So when it's open, it doesn't matter. It's not applied.
Drive battery, but which side is the positive and the battery?
You have to find, okay, so we have the amperage for this side and the amperage for that side, which means that the amperage system in series is equal,
Then you have these two.
right? All the way through. This is just Ohm's law.
Exactly.
So, off, and so you just do your amperage times each of these six numbers, and then it's gonna give you the brightness range. This here, that's the brightness, or the power.
Forget about one. Just always remember. No.
I got a 2.1. Yeah. I think I can get the brightness.
I'm just going to quickly explain what the activity is going to be upstairs. So once you go up, what I want you guys to do is build a Wheatstone bridge. I want you guys to build a Wheatstone bridge using your breadboards, okay? And you guys are going to use resistors, not light bulbs, all right? And what I want you guys to do is to set up a bridge. My marker doesn't work. Let me see if I have some space to draw it here. I want you guys to set up the Wheatstone such that me? Oh no, okay, it doesn't matter. I'm almost done. You have a resistor 1, resistor 2, resistor 3, and here we're going to put resistor unknown. Again, this is the whole purpose of this. Is you're going to put an unknown resistor, and obviously this is going to be connected to a battery source like that, and you're going to measure the voltage across your bridge, and you're going to pick the resistors that you put for R1, 2, and 3, and you're going to pretend, right, because obviously you already know what the resistance values is of all of your resistors, you're going to pretend that you don't know this one for RU. All right. And what you're going to do is you're going to use this Wheatstone bridge to calculate what RU is. All right. And then you're going to compare it to the actual value of RU based on your data sheet. Okay. So the idea is to be able to use the Wheatstone bridge to be able to calculate a unknown resistor. Okay. So we're going to do that. I'm going to head upstairs to get you guys started for those of you who are done. We can start there at 10 o'clock. Half an hour should be plenty of time. If you're done or not done, it doesn't matter. Come upstairs, start that so that I can maybe help you with that and get you guys started. And then at the end, once everything is done, I'll send you the answers on how to do that. In case you didn't figure it out, I'll send you answers on how to do that so you could do it on your own. And so that if it comes to the lab test or any kind of situation, you know how to do it. Okay, so we're going to go upstairs. We'll continue.